Hi everyone. Does anyone misheard me? Is everything cool? Okay. So hi everyone. I'm really glad to be here to talk with you about Leex and Yecc. First of all, my name is Nicolas Boisvert, an Elixir enthusiast. I work as a full-stack developer at Rum & Code in Shawinigan, and I love open source. I love contributing. So if any of you looks for contributors for your projects, don't hesitate. I would love to take part of it. So let's get started. And now maybe some of you might be wondering what they are and what they're used for. We don't hear about them that much when we hang around on Elixir, Phoenix, Ecto documentation. However, they're used in the language itself and in many libraries. So these two have been implemented in Erlang since 1997. Leex is a lexical analyzer generator, so it takes a token definition file in an XRL format, and it returns a Lexer generator. Yecc, for its part, is a LALR1 parser generator, so it takes a BNF grammar and returns a Erlang parser module. I know it's more of Erlang, but you'll see that it becomes really easy to use in Elixir, and it's really fun to use, and maybe very handy. So even though it might be a concern-specific tool, it has many use cases. It may serve as a rule validation system, arithmetic operation of evaluator, custom programming language, or data structures, and lots of things. Elixir, for itself, uses it in its own language to parse the language, and GraphQL Absent uses it to parse GraphQL queries and mutations. Through the presentation, we will be writing a JSON parser using these two. You'll see that it's much simpler than it looks. So the XRL file for the Lexer, it takes three parts. So it has the definitions where you have the token definition. So you said a name and how they were presented. It can be a string or a regex. They are not really regex, but they use the same tokens, so it might be easy for anyone who is used to regex. You have the rules part, as you can see under, where you define how you want to handle some tokens. So for instance, in the up we have digit, which is 0 to 9. We have positive digit, that is 1 to 9, and there it goes. And in the bottom we have an int value, which will return a token, which name will be int. We will put the token lines, so it may be easier to debug, and we will cast the token chars into an actual Erlang integer. So, and you have also, I forgot, the Erlang code where you can define Erlang function to use in the Lexer. They may be really handy, but in the Lexer we will not use anyone, sorry. So for our JSON parser example, these are the tokens we'll need. We'll need curly brackets, square brackets for array, comma to separate values, colon for key value in the object, true, null, true, false, and null, integer with negative integer, floats, and string, which are anything between double quotes. So we have an example here of a JSON, which is a user that has a name which is Bobby Hill, and which has post IDs 1 to 4 in an array. So our basic Elixir file definitions will look like this. So we have white spaces and terminator. We need them because they are allowed in a JSON. Even though they'll be ignored, you'll see later on, but we need to define them. So we have the comma and all the token we will be using in our Elixir. In the bottom we have the combination, which integer and float combination. We also need the literals, so like true or false or null, which are simply string literals. The rule part is what will tell Leex to handle the tokens. So whitespace and terminator will be skipped, obviously, because we don't want to need them. And then we'll have token, comma, which is a token. We will cast the chars into an atom. The int will be cast into an int, the float to a float. The string, we will trim the string because it has surrounding quotes, and we don't want this. We don't want these. So we will have only the clean string inside the double quotes. After that, we have true, which is called to a real true. False also. Null will be cast to a nil. And we have the other token like curly braces or square brackets that we will convert into actual atom. So how you compile these files? Here we have all the lexing part for our language. How to compile it is simply put it in a src folder in the root of your project. Here, as you can see, we have the XRL file, and it's compiled down to an erlang module, just see here, and which is compiled down with the Elixir project to be used in the VM. After that, the module will expose a lot of function with a string that will take a string as an input and return a list of tokens. So, if we take our example here, the Bobby Hill JSON, it will return a clean list of tokens. So as you can see, we made a JSON. We made a char list because actually the Elixir will take a char list as an input, but you can just convert any string into a char list and then give it to the Lexer if you want to. So it gives us a clean token list. If we have any syntax problem here, we will not be notified because this is only Elixir. It gives us tokens only. As you can see, strings are not surrounded by quotes. Integers are real integers, and there it goes. So here's a quick demonstration. So we have the file. Is it too small? Is it okay? Good? Perfect. So we have all the things we saw earlier. So the definitions, we have all our tokens, the rules, we have our rules also. It's nice because VS Code provides a nice syntax highlight for this, so it makes it clear to read, because when I did Java CC at university, I did not have any syntax highlight at all, so it was a pain to work with, which is not the case with Leex. So if I try to execute something, so let's say, for instance, my module now that is compiled will be called with colon and the name of the file, so which is lang. We have all the functions, so we can call, for instance, string with a JSON like an empty object, and it gives us tokens. If I provide an invalid token, for instance, A is not a valid token since it's not quoted. It tells me that I have an illegal character, which is A. But if I surround it, oops, I have an actual string with the unquoted value. So let's move on to the parser. So, but before we start the Yecc part, I think a quick overview of formal languages will be helpful. Programming languages are formal language and are defined by a grammar, which is why it defines a formal language. The concept of formal languages is important in many fields, but some terminology has to be known before going further. So let's take, for instance, a symbol. A symbol is actually a token or a token combination. If you take, for instance, 2 plus 3, which is a term, operator, another term, term and operator are symbols, for instance. After that, we have the reduction, which is the derivation process of a symbol into another one. So, for instance, we can reduce the symbol operation to a term operator term. This is called a reduction. We have non-terminals, which are symbols that reduce to terminals or non-terminals. So, for instance, operation is a non-terminal since it derives to term operator term. And we have terminal, which are symbols that can't be reduced anymore, like term and operator. So if we look at the tree we have here, is the syntax of a JSON object. For instance, we have the reductions represented by the arrow. We have pink squares, which are the non-terminals, and we have blue squares that are the terminals. So for instance, a value can either be an array, an object, or constant, which can be integer, string, float, boolean, and null. An object can be an empty object or an object that has pairs. What is a pair? What are pairs? Pairs can reduce to a pair or pair, comma, pairs. And a pair reduced to a string, colon, value. So it recurs into the top and can be any other value. So we can have a string, an array, a string, an object. And we have the array, which is either an empty array or an array that has list, which is a value or a value, comma, another list. So this is for our JSON example. So the Yecc URL part file is divided in 4 parts. So we have non-terminals that we have to define. Non-terminal is, we only name the non-terminal. You tell this is a non-terminal, this is a non-terminal, and the same for terminals. So you will see in the file that it's much clearer. We will define only the terminal and non-terminal. that our parser will use, so we can recognize them. After that, you have the root symbol, which is the root symbol, actually, the first element that will be reduced. So for instance, it will be a value in a JSON file, because a JSON can be any kind of value, can be either null or in a complex object or an array. And we have Erlang code when we define function to be used in the parser. You'll see that we use some of these in the parser. So this is the beginning of the document. We have non-terminals, so we have value, object, pair, pairs, array, and list, as we saw earlier. And we must end by a dot, because Erlang loves ending by a dot. And we have terminals, which is the same principle, but with the terminal, so int, float, string, bool, null, and there it goes. We also have to note that we have open curly, close curly, comma, colon, even those that we will not really use in the final parsing. And then you have the root symbol part, where you define, as I said, the root symbol and all the reduction in a BNF-like syntax. For those who are not familiar with syntax analysis, maybe BNF tells you nothing. It's actually a way of writing reduction of non-terminals into terminals. It follows approximately this syntax. So for instance, it has an operation that can be reduced to term, operator, term, and we tell Erlang that you want the second value, which is the operator, as the first element, the first element as the second element of a tuple, and the third as the third element. So 3 plus 5 would return a tuple with colon, with atom plus 3 and 5. We can also add a $empty if we want to escape a value. So here is the actual file based on the diagram I showed you earlier. As you can see, a value can be all of these. We can see that in pink we have terminals, and in yellow one the non-terminals. So if we have an object, it can be reduced to an object. What is an object? An object is basically an open curly, some pairs, and a closed curly. I want to handle them here. Yeah, this is not up to date since I updated it this weekend, but it returns an object with the actual object. If we have only open and closed, we return an empty object. If we have pairs, we reduce pairs, so a pair, comma, pairs, we'll put tuple. Put tuple is a function I wrote in Erlang, which for instance, takes a tuple and put it in a map. So if I take the first example of pair, comma, pairs, we'll take the first element, which is a pair, which reduces to string, colon, value, and returns a tuple of the string and the value, the key and the value, sorry. So I have a tuple with the string and the value, and I put it in a map where I will merge with the other map as $3. So if I only have one pair, I will simply merge into a single map and not merging with any other map. So it will go recursively, add the tuple to a map and merge the second one and create a clean map. The same for array, but with a list. So the Erlang code part, I told you were there. So unwrap is a function that I wrote that simply takes a 3-value tuple and return the third. Because as we saw earlier, our tokens are all token name, token line, actual value. And in our final parsed module, parsed JSON, we don't want these. We don't want the key. We don't want the token line. We only want the actual value. So if I give atom string 1 and actual string, the unwrap function will return actual string. The put tuple, as I told you, is the first one is has an array of 1 and take a tuple that has a key and a value and put the key and the value in an empty map. And the second one does the same, but merge also with other map. So if we have 2 pair, the first pair will put the tuple in the map and take the other map that is returned to the second pair. I know it may be confusing, but when you look at the file, it gets a bit clearer and you get used to it easily. So here we have, again, our Bobby Hill JSON example. At first, if I remove the Erlang code function I wrote, it gives me the actual map that not map, but tuple list that we have here, using all the strings and the token line that we don't really want. As you can see here, we have string 1 user, and there it goes. But if we add the put tuple and put tuple and the unwrap function, we have a clean map which represents the whole JSON. So it's much clearer, and it's done by at parsing time. At first, it's funny because, as I said, I discovered the functionality of Erlang code this weekend, so I implemented it this weekend. Before on, I was just rewalking the whole map to convert the key to have only the value, and it was a double process for nothing, since I can do it while parsing and then be more efficient. So let's take another demo. So the parser that we have is the same as you saw earlier. The only difference is that the object here actually returns the $2 parts, so the pairs, which are the map merged with the other pairs. And if we don't have any pairs, we return only a map. This is the map syntax for Erlang, for those who are not familiar. And then again, we put into tuple and we unwrap the first value. Since it's absolutely a string, to be compliant with JSON spec, actually it has to be a string key and cannot be an object key. So we unwrap the first value to get only the string. And here at the bottom we have the actual Erlang code, so the function you saw before. What I did is wrote a basic example here that is a module that parses a string. So if I give it a string, it simply converts it to a char list and pipes it to parse. Otherwise, it lexes the string to get tokens and parses the token. Otherwise, it gives an error. So for instance, I have a lot of tests to test the process. So we have a JSON that has age 25, which return a map, in a lot of example here. So as we can see, if we give it an empty object, it gets an empty map. Key value returns a key value, null converts to nil. A complex object, here we have quiz, math, and questions and answers, and it converts to a cute expected map. So basically, this is how it works. I know it may be a lot of stuff to remember, because these may be not concepts that you're familiar with. If you never did syntax analysis, you might be wondering what the hell this guy's talking about, but I promise you that when you get used to it, you enter it and you start working with it, it gets really much clearer. As I said, I had the occasion to test this at university at my last semester. I had a deal with my teacher that I could use Elixir in school, which is really awesome, because he wanted us to browse the wonderful world of aspect-oriented programming, which don't interest me at all. So he gives me the chance to write this using Leex, Yecc, and a custom parser in Elixir. It's way simpler to write parsers using clean Elixir than using anything else. I tried a bit of Java CC, parselet, and JavaScript 1 also. I can remember the name, but this is the first time that I'd had pleasure writing parser. For instance, I did a PHP parsing package for Mirago's accent, and I rewrite it using the Lexer instead of parsing tokens by tokens like some dirty wizard. So with this, is much cleaner, much maintainable, and much funnier to play. So, so I hope you liked it. I hope it has interested you in writing parsers. If you have any questions, I'll do my best to answer, but if you want to see the final code, it's on my GitHub, so Nicolas Leex, Yecc example, and you have the whole code with tests and things, and don't hesitate to bother me if you have questions. Thank you.